Hello guys, welcome to the series of the pipelining numerical. We will be discussing numericals for this topic. So we will dig deeper into the concepts of the pipelining. So let's discuss this numerical. In this numerical, we are told that we are having an instruction pipeline with four stages: S1, S2, S3, and S4. So these are the stages of the instruction pipeline. And basically these stages as we know, these stages are the combinational circuits used to perform the task associated with that particular stage, and we know that every stage is independent. So in this diagram we can see this is actually a very nice diagram for instruction pipelining. They have given us some delaying circuits also. In the delaying circuits, we are basically having pipeline registers. So what are the pipeline registers? Actually, when the data passed from one stage to another, temporarily we need data to be held somewhere. And to hold that data, we use pipeline registers. So due to these pipeline registers, we get certain amount of delay that we call the pipeline register delay. So after each stage, we can see that we are having pipeline registers, and the delay due to these pipeline registers are 1 nanosecond, and we are given with the stage delays also. For the stage S1 we are having 5 nanosecond delays, then 6 nanosecond, 11 nanosecond, and 8 nanosecond respectively. So they are asking what is the approximate speed up of the pipeline in steady state under the ideal conditions when compared to the non-corresponding pipeline implementation. So because this is the pipeline implementation, so we are dividing our CPU in the various stages. In this particular case we are having 4 stages, but if we don't use pipeline, so in non-pipeline CPU, the CPU is treated as a whole unit. So we have to compare what will be the speed up by if we use this type of organization, and if we don't use this type of organization, then by implementing the CPU in such type of design, how much speed up we gain. So this is the numerical. Now we will discuss the solution. As we gone through the numerical and found that we we have to calculate the speed up. And what is the speed up? Speed up is basically non-pipeline execution time upon pipeline execution time. So what will be the non-pipeline execution time? It will be the summation of all the delays in all the stages all the stages uh, all the stage delay in the instruction cycle. So as we seen, we are having 4 stages, and every stage combined with its register delay is being added together to find out non-pipeline execution time. Similarly, if you want to find out the cycle time in pipeline processor, then because we are having non-uniform delay in all the stages, then definitely we have to choose the delay in such a way so that every state every stage should transfer its contents to the next stage in such a way uh, so that every stage should be able to process the request in a uniform time. For example, let's take an example. If we are having these three stages, and this stage is requiring 2 units of time, then this 3 units of time, and this 1 unit of time. Then what will happen? Uh, in 2 unit, this stage will pass the data to this stage. This is the, suppose this is S2 state, and this stage will pass the data, because the completion time in this stage is 3 unit, so it will pass the data to S3 stage in 3 units. So this stage, S1 stage, pass the data to S2 in 2 units, but S2 will be processing the data, because it needed 3 units of time. So if we send this data in 2 units, then definitely the data will overlap somewhere, or it got messed up. So what we can do, instead of passing the data in 2 units of time, if we pass it in 3 units of time, then see what will happen. So in 3 units of time, this data will be passed to stage S3, and in 3 units of time, this data will be passed to S2, because S2 will be free after 3 units of time. As the data was ready in 2 units of time, but we passed it in 3 units of time. So because the delay was non-uniform, so we have to make it uniform, because the stages should coordinate with each other in such a fashion that their delay should be uniform. So to achieve this uniformity, what we should pay off? We should pay off the time. We should pay off the clocks. Actually, the time is in the form of clocks. So in the case of non-uniform stage delays, what we will do, we will take the maximum clock time of any stage for the clock, and as we are having 1 nanoseconds of register delay in each clock. So because the register delay is uniform, so how we will calculate the cycle time? The maximum amount of clock which is needed in any state. So we are having 4 stages. Uh, these are the different clock times. So we will take the maximum clock time, that is the 11 nanosecond, and we are having 1 unit of delay, so 1 nanosecond for this. So total clock time or total cycle time for the pipeline processor will be 12 nanosecond. Okay, क्या कह रही हो? So as per our talk till now we can see that in pipeline the execution time is one clock cycle. In one clock cycle we have to in pipeline processor we need the CPI should be equal to 1. So because if we need efficiency of pipeline 100%, then clock per instruction should be equal to 1. So in clock one cycle, in one clock cycle, in our previous pipeline design, we can find out that one clock will be of 12 nanosecond. So what will be the speed up? Speed up is actually we have already discussed the formula. It's a non-pipeline execution time upon pipeline execution time. We have seen in our time calculation, then in non-pipeline execution time was 30 nanosecond, and for the pipeline execution time it is 12 nanosecond, and we can find out the ratio, it is 2.5. So our pipeline execution is 2.5 times faster than the non-pipeline execution. So it's the answer is that speed up we will get is 2.5. 2.5 means uh, it will be 2.5 times faster than the non-pipeline execution. Okay. So now we will be discussing this numerical. In this numerical we are given that we are having a 4-stage pipeline processor. So the processor we have considered in this example is a 4-stage processor, and the cycle needed by the 4 instructions. We are having 4 instructions, I1, I2, I3 and I4, and in each instruction the time taken in each stage is given in the tabular form. So this particular table gives us the instruction delay, or we can say the instruction execution time in each stage. So we are having S1 stage, S2 stage, S3 stage and S4 stage. So in this diagram, for I1, instruction I1, they are telling, what does it mean? They are telling that in stage S1, I1 takes 2 clocks. In the similar fashion, in stage S2, I1 takes 1 clock. In stage S3, I1 takes 1 clock. In stage S4, I1 takes 1 clock. In the similar way, if we talk about the I3, in stage S1 it takes 2 clock, in stage S2 it takes 1 clock, in stage S3 it takes 1 clock, and in stage S4 it takes 3 clock. So this table is just giving the stage delay, or stage execution time, or or we can say stage execution time for each instruction. So now this data is given. Now they are asking what will be the number of cycles needed to execute the following loop. So we can see that this is a for loop and this is running from I is equals to 1 to 2. What does it mean? It means it will be running instruction I1, I2, I3, I4 for I equal to 1, and again running I1, I2, I3, I4 for I equal to 2. Means, what does it mean? It simply means that I1, I2, I3, I4 instructions will be executed 2 times in this loop. So they are saying that if we have to run all these instructions 2 times, then how many number of clocks we should be having? How many clocks we should have so we can execute these instructions 2 times. So we will discuss the solution in next slide. Thank you. So in such a questions where we have to find out the number of clocks, we have to design a phase diagram. So generally in phase diagrams, we write stages in columns and clocks in rows. So this is for example, this is first clock, then it is second clock, then it is third clock, fourth clock. In this we will go on writing, because we don't know, as we don't know how many clocks are required. So we will just be adding these numbers one by one till the I1, I2, I3, I4 will be executed 2 times. So what will happen? Suppose we have to, first of all we have to run I1, then I2, I3 and I4. So what will happen? We will try to run these instructions in pipeline first for I equal to 1. For I equal to 1, we will run these instructions. Then what will happen? At first clock, I1 will run. But as we know that in stage S1, I1 required 2 clocks. So I1 will be here and here, because 2 clocks required for S1 phase. Again, after running I1, in clock 1 and clock 2, this stage S1 will be freed. So now the instruction I1 will processed by stage S2. So at this time in clock 3 stage stage S1 will be free. So if stage S1 is free, then we can run the I2 in its stage 1, because in clock 3 S1 is free and S2 is busy with S1, S2 is busy with I1, so we can run I2 in S1 at clock 3. Then what will happen in the next clock, because in I1 required only one clock in S2, then I1 will move to, in fourth clock I1 will move to S3. Okay, and again S1 and S2 are free, because I2 will be requiring only one clock in S1, so I2 will be moved to S2 phase in clock 4, and again fourth clock of S1 will be free in fourth clock, so we can push I3 in its first stage. In the similar fashion, uh, because we know that I3 will be requiring 2 clocks in S1, so I3 will be running for 4 and 5 clock. In the similar way, I2 will be running for 4, 5, 6 clocks, because I2 will be requiring 3 clocks in S2, and because I1 will be requiring only one clock in S3, so it will move to S4 in fifth clock, and after this I1 will finish its execution. So after fifth clock, I1 will be out of the pipeline. So I1 has completed its execution, and again in the sixth clock, I3 will finish its execution in S1, and it will move to S2, and this sixth clause I1 will be free, so we will place the next instruction in this. So in this fashion we keep filling this phase time diagram, as we can see that I1 is completed in fourth in the fifth clock. In the similar way, we can see that I2 is completed in 10th clock. Again, we can see I3 is completed in 13th clock. Then I4 is completed in 15th clock. And again next time, because this execution was for I equal to 1, for I equal to 2, again these things will be happening in our pipeline. So we can see that at 16th clock I1 will again come out of the pipeline, because this I1 entered on the 7th clock. Okay, because this I1 is entered in 7th clock. Okay, and again we can see that the second time I2 entered in the pipeline at 9th clock, and it is coming out at the 18th clock, and I3 is entering in the pipeline at the 10th clock, and it is coming out from the pipeline at the 13th clock, and I4 was entered at 12th clock, and it is coming out from the pipeline at the 23rd clock. So in this way, if we keep on filling this phase time diagram, we will find that because each instruction to be executed 2 times, we can find out the number of clocks required in this fashion. So when we have to calculate the number of clocks required in pipeline processor, we try to just draw a phase time diagram. I have discussed it, and you can see that the number of clock cycles required to execute this loop in which I1, I2, I3, I4 need to be run for 2 times, we require 23 clock cycles. So this was all about the calculation of the clock cycles. Uh, thank you. Thank you class for attending the 2 numericals on pipeline design. If you have any doubt, you can comment or you can ask me on my personal mobile number. Thank you.